Hey everyone, so in the last video we went over some definitions and some formulas involving hypothesis testing and confidence intervals with two populations, and in this video we're going to go over some examples. So let's look at the first example here. So a new lawn care company is developing a new formula for fertilizer. So there are two proposed fertilizers. One of them is fertilizer A and the other one is fertilizer B. And they're tested against each other to see which one is more effective when it comes to removing dandelions from yards. So we have 100 homeowners who are desperate to remove the dandelions from the yards, and they agreed to use the fertilizers. So half of them use fertilizer A and half of them use fertilizer B, and we're assigning them randomly. So after 2 weeks, the users of these fertilizers are nice enough to go out and count the dandelions for us. And we find that the users of fertilizer A have an average of 62.2 dandelions, and the users of fertilizer B have an average of 49.6 dandelions. So from past trials, we know that the standard deviation of the dandelion count for the yards of that size is known to be 32.8. So, assuming that each of the homeowners have approximately the same amount of land and started with approximately the same amount of dandelions, is there enough evidence to suggest that one of the fertilizers is more effective at removing the dandelions? So, first thing we need to do here is always the first thing we need to do. We need to list out the information that we have. So in this case, we're going to have our sample mean of fertilizer A, which is 62.2. We're going to have our population standard deviation of fertilizer A, which is 32.8, and our sample size from fertilizer A was 50 because we had 100 people, half of them use fertilizer A, half of them use fertilizer B. So everything's actually going to be the same for fertilizer B. It's the same population standard deviation and the same sample size. The only difference here is that our sample mean was different. So that's a lot of information, and it's good to write it down because now if we need to use it in a formula, we have it available to us immediately right here. So now let's structure the hypothesis test. So we're testing whether one fertilizer is more effective than the other, but we don't care which direction this is going in. We don't care if fertilizer A is better than fertilizer B or fertilizer B is better than fertilizer A. Whichever one is better, that's one we would like to use as long as it's statistically significant. So we're going to come up with a two-tailed test here because we don't care which direction. So our null hypothesis, which we assume to be true, is that the two population means for dandelion count are going to be equal. And our alternative hypothesis is that they're going to be not equal to each other. And this not equal to sign, remember, is what creates our two-tailed test. Equivalently, we could structure the hypothesis test in this way. So if mu1 and mu2 are equal, that means mu1 minus mu2 is equal to 0. And if they're not equal, then this is not equal to 0. So this is the same thing here as this is up here. It's just expressed in a different way. So we're actually not given a significance level here. So by default, we need to use alpha equal to 0.05. That's what we're going to use if we are not given a significance level, because that is the most commonly used significance level. So since the population standard deviations are known, and both sample sizes from our random sample were greater than 30, we know we can use z here. So the test statistic is going to be this. This was our formula that we came up with in the previous video. So we actually have all of this information already. We listed it out at the very beginning of the problem. So when we plug all of this in, we're going to come up with something like this. And the only thing I haven't talked about so far in this video is that delta 0 is going to be equal to 0. And remember, delta 0 was just the hypothesized difference. In our null hypothesis, we said that mu1 minus mu2 was equal to 0, and that 0 is going to be delta 0 here. So when we plug all of this in, we're going to come up with 1.92, and that's going to be our test statistic. So this is a two-tailed test with a significance level of 0.05. So we're going to have two critical values here since it's a two-tailed test. Our first critical value is going to be Z alpha half, and alpha is 0.05, so alpha half is 0.025. And the value that gives us an area to the right of 0.025 is Z equal to 1.96. And then since it's a two-tailed test and the Z distribution is symmetric, we could just take the negative version of Z alpha half, and that'll give us the critical value on the left side. So our test statistic, remember, was 1.92. So the p-value is the probability of observing something as extreme or more extreme than what we saw. So this is going to be the probability that Z is greater than 1.92, the probability that something is more extreme in the right tail, but we also have to consider the left tail, so we have to multiply this by 2. So when we take that probability, which is 0.0274, and we double it, we come up with 0.0548, which is slightly greater than our significance level of 0.05. So in this case, we're going to fail to reject the null hypothesis. So that means we don't have enough evidence to conclude that one fertilizer is more effective than the other. So we have to be careful here because this is one of those tricky problems. Because if we had forgotten to double this p-value here, we would have ended up with 0.0274 as our p-value. And what would have happened is that since that is less than alpha, we would have ended up rejecting the null hypothesis, and that would have been incorrect. So this is a critical thing to remember. We have to remember that when we're doing a two-tailed test, we have to double that value that we come up with to get our p-value. So this is what's going on here. So we came up with a test statistic of 1.92, and that's where this sits right here. Now our rejection region is going to have an area of 0.05 because that was alpha. But since we're splitting this up into two tails, we're only going to have 0.025 in each tail. So what happens when we're calculating our p-value is we're looking for the area to the right of this 1.92 right here. And that tells us the probability of observing something as extreme or more extreme than this value right here. But since it's a two-tailed test, we have to take into consideration this tail as well. So by taking our 0.0274 and doubling it, we're taking into consideration this side right here. And that will come up with a proper conclusion for us because as we see right here, our critical value is most definitely not in the rejection region. So we know without even calculating a p-value that we would fail to reject the null hypothesis here. So we could also construct a 95% confidence interval here because alpha is equal to 0.05. And this will be a confidence interval for the difference in the two population means. So this was our formula for a confidence interval for the difference in two population means when we were using Z. And if we plug all of our information into this formula, we're going to get this as our confidence interval. Now, the important thing about the interval that we got here is that the number 0 is in this interval. And that's important because if 0 had not been in the interval, then that means that 0 is not really a plausible value for the difference in the two population means, and it would have been reasonable to reject the null hypothesis there. But since it is, that means that it's plausible that there is no difference between the two population means. So that confirms for us that it was reasonable for us to fail to reject the null hypothesis. Now, one thing to note here is that we can really only do this comparison between the confidence interval and the hypothesis test if we're doing a two-tailed hypothesis test, because then both would involve both of the tails. Whereas if we were doing a one-tailed hypothesis test, it wouldn't really make a lot of sense to use a two-tailed confidence interval compared to a one-tailed hypothesis test, because then our results wouldn't exactly correlate with each other. So now let's look at another example. So Mr. Johnson's a high school math teacher, and he's very calm and methodical. And Mr. Smith is a high school math teacher at the same school, and he's very loud and frantic. And Mr. Smith claims that this keeps the students engaged, and he's even bold enough to claim that his teaching style is better than Mr. Johnson's teaching style. So we have some pretty crazy drama going on between the high school math teachers here. So Mr. Smith attempts to back up his claim by stating that his test scores are higher than Mr. Johnson's, and therefore his teaching style is better. So when we look at their test scores, we get this table right here, and we see that from the sample of 21 students in Mr. Johnson's class and 23 students in Mr. Smith's class, we see that the sample mean of test scores is slightly higher in Mr. Smith's class. But as we've seen before, just simply looking at the sample means doesn't tell us whether there's a significant difference between the two, and we need to check to see if there's any statistical significance behind Mr. Smith's claim that his test scores are higher than Mr. Johnson's. So here we're going to use a 5% significance level and perform a hypothesis test for the two population means. So we're testing whether or not there's enough evidence to suggest that Mr. Smith's test scores are significantly higher than Mr. Johnson's. So our null hypothesis, which is going to be our statement of equality, is that Mr. Smith's test scores are equal to Mr. Johnson's test scores. And our alternative hypothesis is that Mr. Smith's test scores are going to be higher than Mr. Johnson's test scores. And here we're going to use mu1 to be the true population mean of Mr. Johnson's students' test scores. So Mr. Johnson is going to be the first population, population 1, and Mr. Smith is going to be the second population, population 2. So once again, we have our hypotheses here, and an equivalent way of listing this would be this. And the reason we might want to list it this way is to get a delta zero. Now, in this case, it's going to be 0, so it's not really going to make much of a difference. But this is one way we could list it out, and that would give us a delta zero for the formula if we needed one. So since we're assuming the students' test scores are normally distributed and that our unknown population variances are equal, we're going to be using t here. So remember, in the formula for the t statistic, we had something called the pooled variance. We assume the population variances are equal, so we pool them together to come up with this SP squared here. So when we plug all of that into this formula, we're going to come up with a pooled variance of 63.04, and we can use that as our SP squared in the formula. So now we can calculate our test statistic. So we take our sample mean from Mr. Smith's class minus the sample mean from Mr. Johnson's class minus our delta zero, which was 0 in this case, over the square root of our pooled variance times 1 over the sample size from Mr. Johnson's class plus 1 over the sample size from Mr. Smith's class. And when we do that, we're going to come up with a test statistic of 0.7313. So in this case, our degrees of freedom will be n1 plus n2 minus 2, which is equal to 21 plus 23 minus 2, and that's 42. Now, one thing we need to be careful with here is that 42 degrees of freedom does not appear on the t-table. So in this case, we're going to need to round down to the next lowest value for the degrees of freedom that appears on the table. So no matter what value it is, no matter how close this might be to our next value on the table, which I believe is 50, we're always going to round down because we don't want to carry on with our calculations assuming we have a sample size higher than it actually is. We always want to be as conservative as possible when we're rounding our sample size. So using 40 degrees of freedom with a significance level of alpha equal to 0.05, the critical value is going to be T alpha, which is the value of T with that level of degrees of freedom that gives you an area to the right of 0.05. That critical value is going to be 1.6839. So since our test statistic, which was 0.7313, is not as extreme as our critical value, which was 1.6839, we will fail to reject the null hypothesis and conclude that there's not enough evidence under the 5% significance level to suggest that Mr. Smith's teaching style is more effective than Mr. Johnson's teaching style. So here's an image of what's going on here. So remember our alpha level is 0.05. So that means the area of our rejection region is going to be 0.05. And this is a one-tailed test, and in fact, a right-tailed test. So this entire rejection region is going to be in the right tail here. And our critical value was the value of t that gave us an area to the right of 0.05, and that was 1.68. Now our test statistic was 0.73, and just by looking at this image, we can see that this is definitely not in the rejection region, so we would be failing to reject the null hypothesis. But we could also use the p-value method and say, oh, well, there's 0.2347 to the right of this 0.73. So that tells us, based on where the test statistic is located and the area to the right of the test statistic, that we're going to fail to reject the null hypothesis. So let's look at another example here. So suppose a company is developing a television advertisement, and it has two locations. It has a Chicago location and a New York location. And each of the locations has developed a different advertisement. So what they do is they gather volunteers randomly and they ask them how effective the advertisement was and whether or not they liked the advertisement. And in the Chicago location, it turns out that 27 out of the 52 people who were sampled said that they liked the advertisement and that it was effective. And 18 out of the 65 people from the New York location said that they liked the advertisement and that it was effective. So what we need to test here is whether or not there's enough evidence to suggest that one advertisement is better than the other and should be used. And in this case, we're going to be using a 1% significance level. So as always, let's list out any of the information that was given to us. We had 27 people who liked the Chicago advertisement out of the 52 people who were sampled. So our sample proportion from Chicago is going to be 0.5192. And in the New York location, we had 18 people who liked the advertisement out of 65. So our sample proportion from the New York location is going to be 0.2769. So remember, we're testing whether one advertisement is more effective than the other, but we don't really care which one is more effective. We're just going to take the one that's more effective and use that. So this is going to be a two-tailed test because we don't care about the direction. So our null hypothesis is going to be that the two population proportions are equal, and our alternative hypothesis is going to be that the two population proportions are not equal. And just like before, we can express this in this way if we wanted to work the delta zero into here. And then again, we're using a 1% significance level, so alpha is going to be 0.01 here. So the first thing we need to do is check our conditions to make sure we can at least assume approximate normality. So the sample is independent because the people were randomly selected. And when we calculate n1 times p hat 1, we get 27. And n1 times 1 minus p hat 1, that's going to be 25. And both of those are greater than or equal to 5. So that checks out. And if we do the same thing with the second population, which was New York, we're also going to find that these are both also greater than or equal to 5. So we can assume at least approximate normality here, and that lets us use Z. Now, remember, since we were assuming our population proportions were equal under the null hypothesis, we actually can bring in what's called the combined proportion here, or P hat C, or PC hat, whichever one you'd like to call it. And if we calculate that, remember, we're just combining the proportions here. We're combining the x's, and then we're dividing by the combination of the n's. So this is 27 plus 18 over 52 plus 65. If we calculate that, we'll get 0.3846. And we need to do that first because that's one of the pieces of our formula for our test statistic. So now we can take this P hat C and plug this into our formula. So when we do that, we're going to put our P hat C here and here. And then when we plug all of our other information into this formula, we're going to get a test statistic of Z equal to 2.68. So remember, this is a two-tailed test. And since we have a two-tailed test, we're going to have two critical values here. And since alpha is equal to 0.01, Z alpha half is going to be Z 0.005, which is equal to 2.58. And since the Z distribution is symmetrical, we can use the negative version of that as the critical value on the left side. And that's going to be negative 2.58. So our test statistic here is Z equal to 2.68. So that means our p-value is going to be 2 times the probability that Z is greater than 2.68. And remember, we're doing this because this covers the area in the right tail, and to cover the left tail, we're going to multiply it by 2. And when we do that, we'll get 2 times 0.0037, which is 0.0074. And that's less than our alpha of 0.01. So that means we can reject HO and conclude that there's enough evidence to suggest that there's a difference in the effectiveness of the two advertisements. And in this case, since Chicago seemed to generate more interest, we might want to heavily consider using the advertisement that Chicago produced instead of the one from New York. So anyway, that's all for this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.